Okay, the next one will invite a younger person, Professor Jie Bao, and he got his bachelor's degree from Tsinghua University in chemistry and PhD from Brown University. Just finished his postdoctoral work at MIT in 2013. So he's going to talk about nano stuff. Please.
Hear me? Okay, so it's a great honor today. And today I want to talk about sensors. Right? I want to share with you a journey from a nanodot to an intelligent sensing toolbox. So let's get started. So these are the sensing capabilities we have, right? We can hear, we can taste, we can touch, we can smell, and we can see. But let's just imagine for a brief moment that if we're losing all these sensing capabilities, right? Just let's close our eyes and think, suppose all we're left with is our brain and our imaginations, right? You feel that we're completely isolated from this world and we're just so incapable, right? It's a terrible feeling. And this is why we need sensing. Sensing is very important. So we build these automated systems to help us to do things, to help us improve efficiency of building, things or do things that we don't want to really do. And just like us, these automated systems need sensors. We also need sensors to help us to sense things we can't really sense accurately in ourselves, like acceleration, or things that we don't want to sense in ourselves, like a hot plate. Also, these, sensing is very important for the artificial intelligence we want to build. If you haven't noticed, actually, we now live in a world filled with sensors. For instance, the smartphone that you take with you all the time, it alone contains some, probably around a dozen sensors in it, right? And take a look at this chart. During the past 5 years, from 2007 to 2012, the market size for sensors, for mobile sensors, have grown at a rate of more than 200%. That's quite large. And in 2012 alone, that year, the market shipped 3.5 billion sensors. And many organizations have predicted that 8 years from now, by 2022, the size will be over 1 trillion. All right, but that number back in 2007 was only around 10 million. But on the other hand, most of the sensors that were that were built into these systems that induced these growths were actually designed and manufactured or existed more than 20 years ago. So why the sudden change, right? Of course, over the years, the development in the semiconductor industry have brought down the cost for chips so significantly, right? And computational resources as well. So it made possible the ideas such as big data, Internet of Things, sensor network, right? Which generated a lot of needs for sensors. But also, another thing has to do with this jump, this sudden increase. In 2007, the world was introduced a new device called iPhone. And that phone has many sensors built in it, which led to kind of a resolution in the mobile sensor market. So what this tells us is that now the market is not only ready, but also eager for sensors. And on the other hand, the market is also very selective. Not all of these sensors have contributed the same, at the same level to the rapid growth of this market. Indeed, actually, four of them have supported most of the growth. And the reason is also quite understandable, very obvious, because they tell us information that we want to, we care more about, like location or games, right? So this tells us that we want to build sensors. We want to build new sensors. And these sensors have to be related to us in a better way. Now it cannot be just simple of converting a physical property into a number that most of us don't know really what to do about. It has to be something more comprehensive, something that give us information that we can relate to more strongly, we care more about. Things like how good this apple may taste, whether there are hazardous materials around us, or what's my health condition today. But for these sensors, you need much more. The sensing technique and the sensor itself are more comprehensive. But there are sensors like this that exist in this world. The problem is that they're just too big. They're just too big, as you can see from here. So the challenge is that we want to build sensors that are much more comprehensive, can give us information that care more about. But also we need them to be small. We need them to be cheap so that we can have them in our pocket with our cell phones instead of sitting in a lab operated by a professional, right? And also so the reduction of the size and cost cannot sacrifice the performance. Otherwise, we just can't do anything about them, with them. And finally, because the market condition that we see, right, the rapid growth and the market is eager for this kind of sensors, we cannot wait so long. We need to have the capability to do R&D and production in very high speed. So these are the challenges that we are facing. And today I'm going to tell you a story, tell you one sensor of this kind, hopefully. And the story begins with light. We all know about light, right? Light has many different colors. And when light interacts with matter, it produces even more colors. Right? And that's the reason why we see all these different beautiful colors. But color are not just beautiful. They are very, very, very useful as well. They can tell us about, they can help us differentiate species. They can help us tell the quality of things. They can also tell us the composition of things. A few examples. These apples, right? Without color, they all look pretty much the same. But with color, it becomes much easier for us to differentiate their species. Another example, these bananas. Well, you might think that you can tell the difference between them, but really, without color, the intensity, the brightness is just intensity. It's one number, it's all relative. If you're taking one banana in front of you, you can't really tell anything. So without color, you can't tell anything, but with color, it relates to you, about how ripe it is, how good it's going to taste, and possibly how long it will last. From flame tests, we know that you can actually tell the chemical composition of things just through colors. So colors are useful. And also colors are much more complicated, or at least a little more complicated than what we see with our eyes. And the reason is this. We know that sunlight has a bright white color, but it can transform to a rainbow which has many different colors. Right? So from this, we know that light might not be as pure as we think it is, right? And we can actually do that, like separate the different colors of light using a prism. And then we can actually measure, how much light for each different color. And you can plot that. Plot how much light you have at each different color. You have this beautiful curve that's called a spectrum, or spectra. So once you know spectra, you know that our eyes are not really good for colors. Let me give you an example. These two colored dots you see, you think they're completely the same. I'm assuring you, your eyes will tell you they're completely the same color. You can't tell any difference. And the reason is this. The way our eyes tell us color is by using three different color filters: red, blue, and green. And our eyes tell us within each color filter or each color beam how much light we're getting. So for these two dots, we have exactly the same amount of light within each beings. Okay, so that's why these colors are completely identical to us. But if you look at their spectrum, they're drastically different. This tells us in our eyes it's just not good enough for colors. We need something that can tell us color in a better way, more precisely. And that instrument, that thing we're talking about is called a spectrometer. So because spectrometers can tell us so much about color and so precisely, and can tell us the composition of things and, etc. It's being used very widely across fields and disciplines such as physics, chemistry, biology, cosmology, medical studies, even environmental sciences. So chemists, they use spectrometers to tell the composition of things, and also outside the academic environment. Government officials and professionals, they use spectrometers to help us guard the food and drug safety. In battlefields, spectrometers can help soldiers to help, to tell their health conditions and to see if they're surrounded by hazardous chemicals. They can be used in, more related to our daily life, like tell you about your skin color and recommend cosmetics. And they help professional artists or painters to match colors as well. In Chinese medicine, the first thing you see a doctor, a doctor will probably ask you to, to let him see your tongue. He wants to see the color because the color of the tongue can tell you a lot about your health condition. And the same thing happens to your urine, right? And all these things, you can tell a lot about their health conditions through the color of it. And also clinicians and doctors. This is just an example of your skin moles. And the color of it can tell you a lot about whether it's, it could be more or a bigger chance of being cancerous. Also, there are examples of just giving you, showing you your pulse rate through the color of your face. Very tiny change, color change. Can also tell you about your blood oxygen level, even your glucose level. We're not completely there yet, but it's also being seriously looking into. So spectrometer can do so many things, but again, it's just too big. That's the problem. So obviously, people have been trying very hard to make them small, but it turns out it's very challenging. Actually, there are some fundamental physics about it that's limiting the performance. Once you try to reduce the size, then the performance just can't catch up. If you keep the performance, then it's just too big. It turns out there's a very strong conflict between size and performance. And people tried many different approaches, but just still, they're not good enough. The best compromise today that we have are these handheld spectrometers. They're being used in many labs, across the world. But still, they're sold at the price above $3,000 US. And they're still far from, small enough to fit your cell phone. So what we have done is that we have invented a new way of making a spectrometer. We used a completely new way, and we used a new material for making a spectrometer. It's something that's never been done and never been tried before. And the material was called a quantum dot. What it is, it's a semiconductor nanoparticle, basically. Typically a few nanometers in diameter. The most beautiful property, most amazing property of this material is that you can simply tune their colors by tuning their size. Like changing their size can change this material's color. And why this is important is that, remember, I just explained to you about how our eyes work, when you try to tell colors. And we can use similar principles. Suppose you have detectors made of these materials, and each of them can tell you, differential information about the color, but like these. But suppose you have many of them, right? Each of them can tell you partial information about color, but if you have a lot of them together, they can tell you the precise color of the spectrum. And because this material can easily give us a lot of different colors, you can simply getting a lot of colors by tuning their size. That way, this way, we can make a spectrometer. And so by combining, the knowledge accumulation for decades that I've been working with this kind of material, and also, extensive effort into, performing research and improving technologies to make this material and technologies more suitable for making a spectrometer. And after years of research, we have made it actually possible to reduce the size of a spectrometer all the way to here. So what you see here is the eye of the needle, and that's the size of a spectrometer that we can build with this principle. And what's better is that we can do this without sacrificing, at least sacrificing a lot, the performance. So what you see here as spectrometers based on this approach, that's quite comparable to their much larger counterparts. From this table, you can see, we won't be going into details, but the performance are comparable to these larger counterparts, but the size are way smaller. So now with that, all these things that we can imagine, we talk about, your health, military applications, color matching, or food and drug safety can be done through this spectrometer, and which can be fit right into your phone. What's even better is that you can make tracking devices, and they can just track your health condition automatically. And together with big data, right, they can, combining all different information from different parts of the body and your environment, how you do your activities, they can tell you a lot of your health condition. Not only can they tell you about your health, but also adds another defense layer to your health system. So now going back to this plot, this figure, with this sensor. Now, because it's much smaller, we can call it sensor instead of an instrument. We think that this curve is said to be changed. And of course, there are still many challenges ahead of us. For instance, we want to improve, have some fundamental improvements of the materials. The engineering procedure, I won't go into too much details here, but I think you get the idea. And finally, I want to thank you for your attention. Take any questions.
I got it. My older colleague wants to manipulate friction so he wouldn't feel pain when he plays tennis. My younger colleague wants to manipulate color so he would always look young. Question?
Tell us how it actually works. So you propagate with a blue laser or something, and then describe exactly what's in
So,
what are you actually doing? I mean, you describe what's actually in the chip. You said there are these quantum sources of light. So are you optically pumping them?
no, we don't pump. Well,
Is there a diode there that pumps the shorter wavelength?
So no, I mean, the spectrometer works, you just take light and you measure them, right?
Oh, it's just absorption.
Yeah, absorption.
So you're using the dots to just absorb.
Exactly.
Just the visible light.
Exactly. Yeah. We don't use emissions because, it's similar. Yeah.
Is this a standard CMOS process, or what kind of a thing?
Twofold. The answer is twofold, right? there are a lot of things we want to use actually to make things closer to the market. We want to use technologies available from the CMOS technology. So we can use the technology we use can be readily adapted to these technologies that we use currently. But also there are things outside, so this material is basically synthesized and processed in solution. It's wet chemistry. So by itself, it's arguably it's a much cheaper way of doing it because you can just manipulate like ink. You can print them onto a surface just like you do with your inkjet printer. So you can print these things directly on top of the semiconductor surfaces that you made with CMOS technologies, for example.
So you actually place different wavelength absorbers in different areas in the laser, or?
Yeah, right. You actually would make a detector array, right? Yeah.
Basically, in order to improve the resolution, you have to have lots of
a lot of them. But it's actually quite simple to do. Comparing to organic dyes, people would think, okay, you can do something similar with organic dyes. Let alone about the stability, right? But just consider the synthesis and processing. Each dye would have a completely different chemistry, right? It would be terrible. It's a disaster to synthesize and to process all these different materials, right? But with this material, with quantum dots, you can actually to prepare a whole solution, and you can watch it react and change color, and you just take aliquots, you can easily prepare a dozen or more just during one synthesis, and all of these things will have almost exactly the same chemistry.
What's the temperature sensitivity?
Temperature sensitivity?
Of the wavelengths?
The spectral range?
Temperature
sensitivity.
sensitivity.
What is the temperature sensitivity of the spectrum? It's how stable it is. You can change the temperature.
The temperature of the device, of the materials. Because here there are two things. If we are talking about emission the emission is typically more sensitive to oxidation, temperature, and all these things. First of all, we're using a much more stable property, which is absorption. But let's go back and just let me explain to you how stable the emission of this material works. Probably, if we go back 5 or maybe 7 years ago, people have been trying to make TVs using the emission of these materials. But it turns out to be a very difficult process because, just like you said, the stability of emission is so in the back of the TV, the temperature can get very high because you need a large lumen, a lot of photons. So stability is an issue. But over the years, through packaging, through the right chemistry about this material, the synthesis, the stability has been worked out. So last year, actually in the United States, a company that previously in our group started, the group that I did my postdoc in, they've collaborated with Sony and launched the TV into the market. So even for emission, that's proven to be stable enough to be in the market. Absorption is much more stable than emission.
Do the particles form sort of a filter for a semiconductor array, or yes?
This is a good question. There are multiple ways. They can form filter.
Or they're active in detection.
Yeah, they can be the active media for detection as well.
But what you have shown here, they form sort of an array of filters.
Right. That goes back to Mr. Deng's question as well. In order to maximize the production, the how it interface with the matured technology, it's just much easier to make them into filters, and they're also much more stable. Yeah.
I'm sure there are more questions, but in the interest of time, let's thank all the speakers again and thank all of you for participating.